And it's recording. Here we go. Exercise 3A. We are now moving into fractions, which requires your LCMs and HCF. So the better your times tables, the better your fractions will be. I like to start off by getting you to think about a pizza. And that's why there's the sort of diagrams for you to understand why the rules of fractions work. Now, the first exercise is called equivalent fractions. Most of us will understand how this works. So here we go. Half. What do you do to get half? You would say that from 2 to get to 4, what do you have to multiply by? Yes, Liam? 2. But then in primary school, they'll likely say, whatever you do to the bottom, you do to the top. And they say, times it by 2. And so 1 times 2 gives you what, Ava? 2. So what they're saying here is that apparently half 1 over 2 is equivalent to 2 over 4, right? And then in primary school, you might have had another scenario. You might say, well, what about 2 to get to 6? 2 times what will give you 6? Let's go with, yes, Ava again. 3. But whatever you do to the bottom, you must do to the top. So then you say, well, 1 times 3 gives you 3. So apparently as well, not only is 1 over 2 the same as 2 over 4, but apparently it's also the same as 3 over 6. Now this is where I question, because this is the whole idea of equivalent fractions. So when they taught you that in primary school, the question is, why is that true? Why is it that if I times it by 2 on the bottom, I have to times it by 2 on the top? Because if I gave you 1 over 2, and then I said, can I add 2 on the bottom, and whatever I do to the bottom, I do to the top, and add 2 on the top? Can I do that? Why not? Because 1 plus 2 gives me 3, and then 2 plus 2 gives me 4. Why is it okay for times, but not addition? See, where'd that rule come from? Why is this happening? We memorized something we were taught in primary school, but why? Why can't we get that right?
Adding changes it completely. Timesing changes the numbers the same way.
Okay, let's stick on that one. When you say changes the number the same way, this is what I'm interested in. Why is it that we know? Think about the very first time when someone came up with fractions. How did they know that if you times it by 2 and you times it by 2 on the top, it will retain the value? How do they know that? They're not magicians. There is a logic to this, and this is what I want to know. Does anyone know the logic to why the timesing works? Leon.
It's cool because you try timesing both the top and bottom by the same amount. So, and the divisor is also the same on the other side. So it's equal. Like it's double the amount.
But then why is it that when I add, I'm adding the same amount on the bottom and I'm adding the same amount on the top? Why doesn't that work?
Because it's like an uneven amount sort of thing. Because if it's 2 and 2 is 4, but when you're adding 1 to 2, it's not multiplying that you only have 3. Right? And since
No, that's okay. So there's a couple of things here there's a lot of gaps in terms of why it would work and why wouldn't it work. The simplest answer to this is this idea, and I'm going to show it to you. This is how you're going to remember it or understand it. This is the theory of fractions. This is where it begins. We started with fractions. Some person said, oh, okay, so we can count 0, 1, 2, 3, 4. We can count backwards, -1, -2, -3. So whole numbers are great. But as soon as we started to venture in between whole numbers, we now have fractions or decimals, right? So they said, all right, I've got a half. Well then, let's think about it this way. What is half times 1? What's that equal to? Half. Okay, so anything times 1, like 3 times 1, that's what we know. 3 groups of 1 or 1 group of 3 is itself. So if I say times 1, it's still the same. True? But then if I asked you, well, how do you write 1 as a fraction? What's 1 as a fraction? Kyle. 1 over 1. So let's delete that and rewrite it again. So apparently 1 over 1 times, 1 over 2 times 1 over 1 is still half. So it should be ticked off. Nothing wrong. True? So this statement is still true. This is still true. Then what's interesting is this 1 here is the most special thing. Because we know that if you times it by 1, it should still be the same. And that's what Elizabeth was saying before, that the value does not change. Because if you times it by 1, it's still a half. But the beauty about 1 is it doesn't have to be 1 divided by 1 to get 1. You could have 2 divided by 2. And what's 2 divided by 2? 1. So if I rewrote this, we know that half times 1 is still half. Well, then who said I can't do it as 2 over 2? Because 2 over 2 is still 1. And then half times 1 is still half. And this is why when you do 1 times a 2, you get a 2. And then 2 times a 2, they know for sure 2 over 4 is actually the same as half. That's where the logic comes from. Because you know that you can times 1. Whereas if I show you now, if I added 1, it's not the same. 3 plus 1 does not give you 3 again. It gives you 4. That's why when you say half plus 1, it won't work because half plus 1 is actually 1.5. That's why it's not the same. And that's why we say, well, when you add them, even if you wrote it as a fraction, it doesn't make sense. 2 plus the 1 and a 1 plus the 1, it's not going to work. That's one of the theories. Okay, so first concept that I want you to take out is why do you have to do to the bottom and then you do to the top and it only works for times? The reason why is you're really just doing multiply by 1. That's the reasoning. Number 2, which is where Ava was almost getting close to what I wanted you to understand here. Theory number 2. This is why the pizza diagram is going to help you understand now. Theory number 2 is when you say half plus 1 over 1, notice that the answer turned out to be, and this is not how you actually add fractions as well, but someone was alluding the fact that 3 over 4 is not the same as that denominator of 2. And the reality is, what does that mean in real life? This is what it means. Here's your pizza. I'm going to delete all of this now. Here's your pizza. You got one whole pizza. I haven't cut it yet. As soon as I decide to cut this pizza with one cut, how many pieces have I separated into? 2. So I've got 1. I've got 2. So a total, so I've got 2 pieces. And when I grab a piece, which this entire piece, if I said I had only 1 piece of pizza, you're like, oh, there, that's cool. That's not a lot. But it depends on how much is 1 piece. This 1 piece is what we call 1 out of the 2. Yeah? So that's 1 half. That's half. So when you say, I picked out 1 piece and I said, how much is that? And you're like, half a pizza. I'm like, whoa, that's a lot. Because what I'm seeing is I'm saying you've got 1 pizza, you cut it into 2, and you took 1 of that away. That's a lot. Versus if I did 2 cuts, 1, 2, how many pieces of pizza do I have now? 4. So I've got 1, 2, 3, 4. Now in order to eat the same amount as what I did, so let's say I come in, Mr. Tran picks up 1 piece, and this is my 1 piece. That's my 1 piece. Like half the pizza, yeah? I'm trying to draw half a circle, yeah? And then someone else comes in. Let's say Elliot comes in. Elliot comes in, and this pizza is cut into 4 different pieces, and he's like, whoa, Mr. Tran's beast. I want to copy him. He wants to eat the same amount as I do. Now, the only way to eat the same amount as I do is if he grabs only 1 piece, because I said, I only ate 1 piece. And he's like, yeah, I'll eat 1 piece as well. Now, if he eats only 1 piece, this is how much he eats. It's not the same. He has to eat 2 of these pieces to make it the same as the amount that I have. One of the key differences here, right here, which we already know 2/4 is the same as a half. One of the things you need to understand is the denominator. When you write 4, 2, 6, these ones 8, and this is 10, you have to realize that these are different to each other. It's as equivalent to saying this table is different to that table. they're not the same. If I asked you how many tables there are in this room, you could say, well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 student tables and 1 teacher table, right? Same thing with fractions. When he's eating a pizza, Elliot's eating a piece of pizza, he's not eating the same piece that I am. This is why you can't just go half plus a quarter, because I'm eating a different type of piece and he's eating a different type of piece. That's why one of the first skills that you need to learn was in order to add and subtract fractions, they need to be the same piece. Just like these tables, they have to be the same types of tables for you to count them together. Same as the chairs, they have to be the same type of chairs. So every fraction that you're seeing here, even though they're equivalent, 3 over 6 is equivalent to a half, 4 over 8 is equivalent to a half, but don't be fooled. Each piece of the pizza is different. This is not the same. You having one of these, 1/8 of a pizza, is not the same as you having 1 out of 2 pieces. That's why you can't add them if the denominators are different. That's why they used to say in primary school, they say you can't add or subtract unless denominators are the same, because what they're trying to tell you is that each piece of a pizza is so different, you can't collect them together. It's not the same. Just like when you're counting the books, right? So, one of the first skills that you needed to understand is, well, then how do you convert these fractions so that you have the different denominators that you need? That allows you to do 3b, add, subtract, then multiply, divide. But the first step is simplifying. Okay? So today's lesson, I taught you a bit of theory. I taught you where and why you have to times top and bottom. The reason is because you're just timesing it by 1. Number 2, why can't you just add bottom and then add top? Because these are actually 2 different pieces. This is 1 whole pizza, and that's a pizza that's cut in 2. Those are 2 different pizzas that you can't say, yeah, I had 3 of those. I didn't have 3 of those. I only had 1 full pizza, and then I had 1 that's half of a pizza. That's why I can't say I have 3 of either. I had 1 that's half, and I had 1 that's full. Yeah? So, today's lesson, if you didn't understand the theory, if that confused you, if I pushed you a bit too far in the theory there, this is all you need to understand. Fill this in. Each fraction with a different denominator, fill that in, write that in. And denominator just means the bottom number of a fraction, is a different type of fraction. You need to understand that. That's going to be the first thing. Every fraction you see, if the denominators are different numbers, they are not the same fraction. They are different values. Just like a pizza, they're not the same size. And hence, it's a different value. That's the first thing I want you to write in. So today's lesson, even if you didn't understand the theory that I just described, let's do the technique. This is the skill. They want you to rewrite in this example 1, you've got 4/5. Now this is a pizza cut into 5 pieces. This is a pizza that's cut it into 50 pieces, which is like very tiny. But they want to know, if someone came in and there was a pizza that was cut up into 50 pieces, how much do you have to eat to make it the same as 4/5? And so we use the same technique again. Yes, Elliot, what are we thinking?
Close to 45?
Close to 45. That is true. Close, but that's not the exact answer. I want an exact answer. Wilbur? 40. Now, how do we get there? The first question you ask is, well, how do I get from 5 cuts to 50 cuts? Think about it. 5 times what? Because we're timesing. We're not adding. Remember, timesing keeps it the same, yeah? So 5 times what gives me 50? 10. But whatever you do to the bottom, you have to do to the top. Because remember, what you're really saying is this. 4/5 times, and if you know that if you times by 1, it stays the same. So if I'm timesing by 10, the only way that this is going to end up being a 1 is I need a 10 on 10. 10 divided by 10 will be 1. That's why whatever you do to the bottom, you do to the top. This is how you get 4 times 10 is 40, and 5 times 10 is 50. So what you now know is that if someone had cut up a pizza into 50 slices, you would have to eat 40 of those slices to be equivalent to having 4/5 of a pizza, meaning a pizza that's cut into 5 pieces, and one that's cut into like 50, you'd have to eat 40 of those out of the 50 to be the same as eating 4 out of those 5 slices. That's what it means. Okay? All right, here we go. Let's practice the skill again. So if you can times, you can divide. 200. How do I go from 200 to 50? Can I please have, let's go with Hashwan. How do I go from 200 to 50? What do I do? Times or divide? Divide. What would I divide by? Can I please have Lucas? 4. 200 divided by 4 will give me 50. And if I know that I'm dividing by 4 on the bottom, then I would. Very good. And 80 divided by 4 gives me what, Liam?
80 divided by 4 would be 100.
Beautiful. This is answering the question. If I want a denominator of 50 and I had a fraction of 4/5, well, 5 to 50 I times 10. Times 10 to the top, it's 40 out of 50. Here, if I wanted 50 as a denominator and I had 80 over 200, well, I know that I had to divide top and bottom by 4 and I get 20 over 50. Let's go to example 2. I'm going to give you, let's make it 90 seconds. I'm going to pause the video. 90 seconds to fill this in. Let's go. 90 seconds and I'm going to call 1, 2, 3, 4 different students.